Thank you for the invitation. It's very good to be here. So, my talk is with Steve Donkin. You know that. And the first thing that I will do is summarize Steve's talk, because seriously, I didn't know where he will finish, and I will do it for my own sake. So, Steve's talk. For each lambda, we have multi-sequences. Right. And these R is going from 1 less than S here, and I is from 1 to lambda S. And this multi-sequences satisfy certain relations, and also they form a vector space altogether. That we denote by lambda. And the point is that we have a surjective map K map from the lambda here, and the kernel is the the space generated by the standard one I will keep ST. I don't want to talk about STDs in the morning. Here, with this be defined like this. So this is just one number, the standard multi-sequence is for all your choices of R and S. Right. Now, the other point was that we have partitions that we call them James. If lambda I plus 1 is less than this number for every I, and this is equivalent to say that the standard multi-sequence is just a big fat 0. Right. And now if I put this together, and this observation, we have the formula that Steve wrote down, that the dimension of the extension space that we want Now here you have a surjective map, so is the dimension of this take out the dimension of the kernel. When it's James, there is no kernel. So here you have the dimension lambda for lambda James and dimension of a lambda minus 1 otherwise. Okay, this is the only thing that I want, actually, from previous talk. The point is that what all these constructions suggest, what we had to do, is to know that now the dimension of the extension space that we want to find is the dimension of the space of multi-sequences, satisfies certain relations, so go and find all the multi-sequences. That's what we had to do. And that was what we were staring at for 8 months. Find the solutions of these things. And Steve wrote down the result when we have 2 rows, and that was easy. And it was easy to check also because we knew current's result. And then we translated current's result was for SL2, we translated for GL2, and then we say that, look, what we get with our method is the same what we get with from current's result, and we were happy. But now we had to move on and go to more rows, and there were 2 paths. The first path was to go to somewhere safe. I explain myself. So from now on, lambda is your partition. We assume that it has more than 3 parts, and always we use d for the degree of lambda. So the first safe path is that we go for partitions that we know how they look like. So the James partitions, they satisfy this property, so we know how they look like. And the point is, can we find the dimension, the sequences for these partitions? Can we find the dimension of this cohomology? Yes. So we studied carefully the 3 parts. And the thing here is that for certain partitions, we found that you can have dimension more than 1. But it was just 2, which is not so bad. The point is that there is a bound. Take n parts, then the dimension for James one is lesser or equal to n minus 1. And then we knew that we can find a partition for 3 rows that has dimension 2. And the point that this bound can be achieved. Actually, we can find a partition that has n minus 1. And it's a very easy one to describe. It's exactly dimensional. The point behind this is that you have all these multi-sequences. These multi-sequences, if you think them about consecutive rows, these are just standard sequence, the extension sequences. So you have one for each pair of rows. What you have to do is to see if they kill each other, if all of them survive together. And for this partition, all of them survived. And you get this one. Right, we could do better than that. We have a solid formula for the dimensions. When your lambda is James. So that was kind of a safe path because we knew how the partition looks like. The scary monsters are when you have to move to the other ones. The partitions that they're not James, so you don't have a clue how they look like. So I'll kill James here. Is that me breathing? Yeah. Right. Yes. What can you do? Let's do more of James. What can you do when you don't know anything about your partition? So I think that was about the third part of my talk. I will stick with this now. Lambda non-James. Right. That lambda is non-James means that there exists at least one pair of consecutive rows of lambda which is not, let's call it the James pair. At least one. And the first result is that if there is one more, if you have two of them, non-James, and something else, that I need this guy to be a little bit further away from R. Then this is 0. Right. This result was known. It was known by Weber, or Weber. And we have a different proof. Now, I hope that this will answer Karen's question. Weber's paper for this result is brutal combinatorics, 20 pages, very, very complicated. Our proof for this result is 3 lines. And I'm serious with the 3 lines. If I have time in the end, I will prove it in 3 lines. Anyway, so this now gives you something about your partition. So now this will be my drawing board. And my goal is to draw all the partitions that they have cohomology here. The Specht models have cohomology. So what it says that candidates for non-zero extensions, for extensions if you start with your partition somewhere here, find your first non-James pair. That would be here. Let's say. So that's my R. And R plus 1. Then, OK, you have the R plus 2. You cannot do anything about it if it's there. But afterwards, the rest of your partition, whatever it is, should be James again. This is what exactly this result says. It says that you will find a pair that will be non-James. Then everything that can go wild will be here in your 3 rows. Afterwards, you must have again James partitions. So this put your partition a little bit, you can visualize now that you corner it. My favorite result, though, for this paper, and I think that that was what made the situation a little clearer, it was the next one. Let, again, your partition lambda take our minimal such that this is not a James pair. So our minimal means that I run from the top of my partition down. I found the first pair that is not James, flag it there. Then we have inclusions, embeddings, this vector space of all the multi-sequences that we're searching is embedded inside here. Of course, in order this to make sense, I need R less than n minus 1, but this is not trouble, this is not a problem at all. If R is n minus 1, even better. Let's go somewhere smaller. Right. What this thing says now says that if I start with a partition that I know that is non-James, find the first pair of rows that this is happening, then everything is controlled by these 3 rows. Everything. What I mean if r is less than n minus 1, and the full thing is here. If r is minus n minus 1, I didn't tell you what's d prime, but you can guess. For the first case, it counts exactly this degree. And for the second case, this one. So the extension actually is fully controlled in my picture here. So if I need candidates for extensions, I must have that this partition here, let's fix the definition to say that a partition that gives you extension is non-split. Steve said that if a partition has extension 0, then we'll call it split. So the logic thing to do, we call the other ones non-split. So I need, for the candidates, this bit to be non-split. Right. And the good thing that this is a very strong result, in my point of view, because somehow it tells you to take the full thing and just look the 3 rows. But also the other good thing is that with all this technology of the multi-sequences, this proof is again 4 lines. So it's not a complicated proof at all. And this is where the joy stopped a little bit when we worked on the paper, because everything was running smoothly and very fast, obtaining such results. But then we realized that, right, you have the non-James thing. Everything, if you need cohomology, it means that you must have a non-split triple, and a partition with 3 parts that gives you some extension. So find them all the 3-part partitions. And that must took the 5 of the 8 months, right, to find all these 3. But we did. We succeeded. I will come to this. That is back to joy again. So it was joy. It was then some, a lot of calculations and everything. And then when we obtained what we obtained, then back to joy. It was like listening Wagner. Dun, 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 dun. Yeah.
Do we know the right-hand side is at most 2 at Specht?
Sorry?
Do we know the right-hand side is at most dimension 2 at Specht? Or did I misunderstand?
The right-hand side?
You just wrote it off.
No, you don't know that it's at most 2.
Ah, okay. Okay.
They were. It's at most 1. Yes, but you don't know it yet. This is. I haven't. That was the James ones. Yes, that's the non-James ones. You don't know anything about it yet. So the thing was that took this long period to talk about the next step, find all the triples. This is how we refer to them: lambda, lambda 1, lambda 2, lambda 3. Where this will be non-zero. Oops. And there are 10 types. with this property. And this, you can write them down precisely how they look like. And the good news is that for these, you have that this is K. So it's one dimension. And this is amazing because here is somehow you start with be very depressed for a partition that you don't know anything about. But in the end of the day, you have this corollary saying that if lambda is a non-James partition, and I know that you will scream about it later because you taught me not put things before people's names, non-James, some James, and I already said before that I will kill James on the board. Anyway, if lambda is a non-James partition, then this dimension is at most 1. Because you have an embedding. The embedding is happening inside your triples, and your triples have at most 1 dimension of homology. So the next step again, find those with x1 to be exactly 1. And then you look at the diagram again, and you say, what is the missing ingredient? What is the thing that I don't know? I know this guy is James. This here is James, because this is the first point that I don't have James. I know that from here and down, this is James. So the only missing ingredient is the connection. What about here? It is James from this row and down. You don't know these two. You don't have a clue about these two. So I will call this the connection informally. And now I can tell you what's the result. If and probably I will express it for p greater or equal to 3, though it's similar for p is 2. So the game is we are in the situation that we have James, James, non-split triples, and we want to test which of them survive, and everything kind of control this connection. If the connection is a James partition, then for all the split triples, for all let's write them down. This is the non-split triples. We have that the full partition, forget the dimension, we don't need it. this thing, it is this thing, which is K. Every non-split triple survives with one exception. So if the connection is James, then actually this embedding is an isomorphism, everything survives, and you have one-dimensional extension. But there is one triple that doesn't do the job. It needs some special treatment. It needs an extra property. It's not that this will give you 0, but you need an extra condition for only one for the 10 triples. Yes. Yes. Thank you. This is my connection, the diagram, yes. Right. What if the connection is a non-James? So I'm looking at this connection here, and if it's non-James, then you go to the other extreme. Everything dies. But of course, you need one exception. So if the connection is James, all the non-split triples will give you, for the full partition, extension, and it will be one dimension. If the connection is non-James, then there are no extensions, apart from one triple, the one non-split triple, that actually survives. And you can see, easy an example of this. P is 3. And take this one. In other words, in symmetric group theory, this says, and you'll see that here you have a K. And you can see that here you have your 3 triple is the 1, 1, 1, which is non-split. And your connection is the extra row. So this is your non-split triple here. And this is the connection, which is not James. Anyway, so there's only one exception that's happening. And this is the full result. Now, I have plenty of time, so I can give you applications of this result. And also talk a little bit about, everything is fine in characteristic p greater or equal to 3. You know now everything. You know that for James partition, you always have non-zero cohomology. You know exactly which are the dimensions. They know that they like to party and they can go wild. For the non-James one, you know exactly which are the non-vanishing ones, and you know that they're kind of miserable and they're always K. So you know all the picture. What about characteristic 2? unfortunately, in characteristic 2, GLN and symmetric groups, they don't getting along in X1s. You have that the dimension of any partition here is less or equal the dimension of the cohomology. And you have an example in hand when you say that even for S2, you know that the H1, sigma 2, this is K. What I'm saying is that there is a self-extension of the trivial model, and this is one of the bizarre things that's happening in characteristic 2 for the symmetric groups. But when I'm in GLN environment, this here what Steve said from Kep's vanishing theorem, if you want to see it like this. And whoa. I'm not allowed to do this stuff. So you know that in characteristic 2, actually it's an embedding. And the embedding is real. It's happening. However, if you have non-zero extensions for the GLN, you're pretty happy to use it and say that I have non-zero cohomology for the symmetric group. Don't go the other way around for characteristic 2. It's not working. So it needs some special treatment here. That's one of the remarks. The other one is about some handy outcomes that you have from all these descriptions. Yeah. Take P greater or equal to 3. And a nice class of partitions are these that all the parts are divisible by P. So your partition now is P lambda 1, P lambda 2, P lambda n. So everything is divisible by P, all the parts, and take n to be greater or equal to 3. Then use the description that we have for the cohomology. This is 0, always. All the partitions that are divisible by P is 0. They don't have any cohomology. Now, I want to mention this because this does several things. First, it strengthens a statement of Hammer. In one of his papers, he states that why?
Go ahead, put it up.
Why?
That 0 equals 0.
Yes, but you state that one of your papers the result is that actually I don't care how many times I divide the rows, right?
Right.
I was using it in a good way. And it's true, since everything is 0. The other thing, though, that you do in this paper is that you also make a conjecture about when the cohomology would be non-zero. And you say that okay. That if lambda is a partition with the simple model for GLN is a composition factor of a symmetric power, then this must give you non-zero cohomology. These composition factors are well known by a work of Kropp and Sullivan. They describe explicitly which are the composition factors of the symmetric powers for GLN. And the counterexample to this conjecture this thing here for lambda, let's say. Is a composition factor of the corresponding symmetric power but the result is that I cannot have things that everything is divisible by p. So this is the counterexamples. And I think that sorry?
So if H1 is non-zero, and now you add a really big power of P to the first part, then
No, it's not. Again, no. That they stabilize if you move forwards, you mean?
right, like the first row.
Yes, it's not. It's, the thing that you say is kind of a James thing for the homomorphisms, right? That you add the first row and you can do it. But do you remember that for the James ones, right?
So it would be the non-James one for that doesn't work.
No, you can use the James ones for, let me. The cohomologies, I said, you can go really, really wild for the James ones. So these guys, right? What was it? N minus 1, N minus 1 minus 1. This has dimension N minus 1. So you can see if I add one more row, the next one, which is a p to the n plus 1 minus 1, I will get cohomology n. And I can do that forever. So the cohomology does not stabilize for these ones.
You added a big power P to the first row.
A big power of p to the first row. To which partition?
To one, like any partition, it would cohomology stabilize. Just make the row longer and make the first row longer by a
Oh, I think, so to the first row you add there. Oh, I have to think about it.
And if you notice, over here on the right, you have your connection, but you don't really know what's going on in the row above. So you can, R and R plus 1 can be bad however you want.
So R plus 1 and R plus 2 together are the non-split triples. Yes, when you start studying this non-split triple, you study with baby steps. You say that the only thing that you know is that it's a non-James, right? So you say that the next good thing, it will be if they are pointed. That's Steve said. And then if
Your answer depended on the connection, so you can mess up.
no, it depended on the connection when I figured out which are all the triples that are non-split. First I had to do that.
So
And
R plus 1 do matter.
Yes. Oh, it's the 6 months of the 8, the RR plus 1. This triple here is the 6 months of the 8. Right. I don't have anything else to say.
So do you know this conjecture of Geranios that?
It's about the simple ones, right?
Yeah.
Yeah. Nope. We never tested, but anyway, it wouldn't go, I guess, because the Geranios says that it's less or equal to what?
It just says some bound, so you've got n's.
Yeah, but for the bound that the big cohomology comes from the James ones, and the James can never be simple because they contain, as Steve showed, a trivial model inside.
But you can go from the finite, from the algebraic group to the finite group of Lie type and get the same. If you've got n minus, if you've got a big thing for, if you've got a big cohomology group for the algebraic group, you can get one for the finite group of Lie type.
But still, I will need simple models.
Yes, so I guess you can't go to some.
No.
So another thing I like about James Control is that it's sort of local, right? You can check the partitions by looking at pairs. So now you're really kind of saying H1 is local also, right? You can run along your partition with 3 and you can tell.
Yes.
Do you think there could be some general result?
For Hn, you mean?
That it's also depends only on.
I don't go there.
I'm not saying you should compute it. That was maybe 20 years for H2, but.
No, I will not say something like that. I don't know. I never tried to do the H2, so.
Yeah, I wouldn't. I think this is the end of the real line of actual computation, but some general result about it. For whatever reason, you don't need to look at parts far away.
Yeah. No. For P is 2, you know that everything that comes from GLN will count for the symmetric groups, right? But sorry?
You have some information.
Yes, but yeah, you need some special treatment there, I guess. But a nice remark about the P is 2 for the symmetric groups is that if you have your partition for the Specht lambda, then because when you dualize it, actually the only thing that you do there is transpose your partition, because there is no sign, then for all the Specht modes that phenomenologically they are not coming from GLN, you can check the transpose partition if it comes from GLN and take all the results that you wanted. I don't know if this is going to be a full answer, what I'm saying, that's only the transpose, but it will give you even more from lambda that come from GLN. For the James ones.
And if it's less than n minus 1, then there should be some multiple x between some simple and k.
Yeah. Yeah, that would be. No. Yeah.
Do you think these items also work for Hecke-Rashbitz?
Yeah. Yeah. Whatever you do with GLN, you do it for QGLN afterwards, and then you throw it to Hecke algebra, right? And obviously, we know, I think that's safe to say that we know how to do it for Q. The quantized work for GLN. However, we would like to have something simple, not run the same calculations. Again, the paper is already 96 pages. I mean,